Hey everyone, this is Dr. Walker. This is video 541 called Microscopic Model of Current. So as the title implies, we want to look at a microscopic view of current. And what that means is the first thing we should look at is the flow of charges. Our charge carriers in our metals are the free electrons. So charge carrier is what's carrying the charge. And we want to know, well, how fast do these electrons actually move? It turns out that the electrons in a conductor, if there's no electric field, these electrons are just going to undergo random motion. They're going to collide with all the other electrons and atoms, and their average speed is actually going to be zero, their average velocity. But once you have a potential difference in a conductor, that sets up an electric field, and we know our negative charges experience a force opposite the electric field, so they will move against the field and they will have a certain drift velocity, v sub d. That's what we want to look at in this slide. So to find an expression for v sub d, we first want to define n, lowercase n, as the number of mobile charge carriers per unit volume. And again, the charge carriers in the metals, which is what we're dealing with here, are the electrons. So first, let's get an expression for the amount of charge that is moving through a conductor. And let's look at a conductor here, which is cylindrical, having cross-section area A. And let's look at the motion of the charges moving a length delta x. All right, so the charge Q is going to be equal to the number of mobile charge carriers per unit volume times the volume, so that gives you the number of charge carriers, times the charge of the charge carrier. So that's the amount of charge. So the volume is, if we're considering a cylindrical cross-section here, is going to be the area times delta x. So NA delta x times Q. And if we're saying that the charge carriers are moving with a speed v sub d, then we can say that the length traveled, delta x, is going to be v sub d times time. So we're going to have NA v sub d times how long it takes to move that distance times Q. Now we can get an expression for the average current, which is the charge, total charge per time. So we just divide this expression by time, and we get NA v sub d Q. So this is our expression for the average current in our conductor, and we can also derive an expression for the drift velocity by solving for v sub d. We get the average current divided by NAQ. So we're going to do an example in the guided examples, but we're actually going to see that this drift velocity is very, very low. It's on the order of 10 to the negative 4 meters per second. Let's look at one more thing, and that is current density. Again, we're looking at a microscopic view of current, and current density is defined as the current per unit area. Current density is actually a vector, unlike current, which is a scalar. The direction of current density is in the direction of the electric field, and this is because when we're looking at current, we're looking at the flow of positive charges, and we know that the positive charges move in the direction of the electric field. If we use our equation that we just derived in the previous slide, that the average current was NQ V sub D times A, and we divide that by area to get current density, we get NQ V sub D. The units for current density is amps per meter squared. Now this expression here for current density, it only gives us the magnitude of the current density, and it's only valid when the current density is uniform and moving perpendicular through the area. Our book actually gives us an expression, I equals the integral of J dot dA. Because the current density is not always going to be uniform, it's going to vary from point to point. The number and the magnitude of charges moving varies from point to point. So we do have another expression that relates current and current density, and it should look familiar to you. It should look like electric flux, right? Electric flux was the integral of E dot dA. But if you remember, for electric flux, we said that if the field was uniform and perpendicular through the area of that Gaussian surface, we said it was equal to E times A. So it's the same thing that we're doing here. We're not going to look at this more complicated expression that tells us that the current is a flux of the current density, but we're going to say, well, if we have a uniform current density that is perpendicular to the surface, that cross-sectional area, then we can have I equals GA, and so that is the expression that we're using. But current density is a very important quantity that we're going to see several times throughout the course. So I wanted to give the general definition over here, but we're not going to use it in this course. We're only going to use the simplified definition.